Hey everybody, back in business here in Roswell, trying to finish off this section on LHospital Rule. Now, let's see, where did we leave off last time? Okay, here we go. Y'all, I'm going to go ahead and take a stab at this one right now. Now, y'all remember that LHospital Rule, let's go ahead and restate that before we start this particular problem. LHospital Rule says that if you have limit as x approaches any number at all, we'll just say as x approaches a of f of x, and a can actually be infinity here also. But okay, it's a quotient. It's called an indeterminate quotient. Now, as long as this is in the form infinity over infinity, or 0 over 0, okay, then again, I beat this to death last time we talked, but this is equal to the limit as x approaches a of f prime of x over g prime of x. Okay? And again, not the quotient rule. I don't think I've noticed any of you guys fall into that trap. There's a temptation to try to do the quotient rule. You know, g squared at the bottom and then low d high minus high d low sort of thing. But remember, you're not asked to find the derivative of the quotient. You're asked to find the limit of the quotient. So this is much simpler than doing the quotient rule. And the quotient rule is ill-advised on a problem like this, even though it's tempting. Now, so let's take a look at this problem right up here. All right. Now, notice this is in the form infinity minus infinity. So it's not currently in this form or this form. So please, please, please don't on the final start taking derivatives of this. Okay. It's tempting to do that. You know, like I told you in class, if the only tool in your toolbox is a hammer, the whole world looks like a nail. Make sure you mold this expression into something that fits this form. Okay. Now, towards that, I'm going to write this down. I'll just recopy this. Limit as x approaches infinity I lost my blue marker, folks. Minus x. I didn't actually. Now, all right, folks. Now, again, this is in the form infinity minus infinity. So this is not in one of these two forms. So the question becomes, what can we do? Y'all, let me shove this up here. All right. So what can we do to make this happen? Make this is crazy. It's like a million miles. This infinity minus infinity. What? How do we make it look like that? Well, I think you guys probably, some of you have already ringing in on this thing. Remember what we can do, which is a clever little trick. We exploit an algebraic truth called the difference of two squares. See, it's just amazing how one very straightforward idea just kind of cuts the boundaries of a lot of different problems. I'm going to put the plus x here. See, remember, like they call that the conjugate back in the complex numbers days. So anyway, we just changed the sign, flip the sign. Okay. Now, again, this is what I've had people call a cleverly disguised version of 1, right? So it's okay to multiply anything by 1. Something divided by itself is always equal to 1. So even though it looks like we're butchering this thing, you're actually doing something legitimate algebraically. Now, why are we doing it? Well, it's that standard thing. This may be the single most popular or useful identity in all of algebra as far as calculus goes. Okay, folks, that's equal to a squared minus b squared, right? And again, you know me, I'm neurotic about this. I don't want people memorizing anything. I want you to see what motivates this. This is this part right here is the algebra that motivates this monstrosity here. Okay. Now, and y'all have been good about this. Keep writing the limit down, please, people. Please keep writing the limit down. Sorry, y'all, I'm having the same problem. Y'all turn it down. Over there. Sorry about that, y'all. So, y'all, what I was saying was back to keep writing the limit operation down until you actually complete the operation. Now, right over here, folks, this would be your a minus b, and that would be your a plus b, right? So this is all going to wash out to x squared plus x minus x squared all over so we got this going on. Now, again, y'all, go ahead and verify this on your own, but this part right here is literally your a squared, and this part right here is your b squared. And again, it's so useful to have this thing at our disposal. You don't want to FOIL that out and multiply it out by hand. I even know teachers that still will multiply this out by hand because they don't trust this. Okay? Now, so what does this end up being? Well, it's a fraction, first of all right? And it looks like it's still infinity over infinity to me. But let's just go ahead and keep writing. Y'all probably like that song. Somebody's favorite. Okay. So, all right, y'all. Now, if you take a look at this, it's definitely in the form infinity over infinity. This is just a line that gets bigger and bigger, and this object here is certainly going to get bigger and bigger. So you see, this is still in the form, or now in the form, thank goodness. So you see why we're dragging ourselves through all of this muck here? We started out with this object that wasn't anything, it's not very tractable, it's not what we wanted it to be, but now through algebraic manipulation, we actually have it in L'Hopital's form. Okay, so it's infinity over infinity, and we can apply L'Hopital's rule. So here we go. All right. Now, what does it say? This is our f, this is our g, right? So let's take derivatives. Very good friend of ours if this derivative is just equal to 1, right? We got numbers to go by now. All right, now, okay, this bottom part, the derivative of the bottom part. You guys remember we've seen this over and over. This is something raised to the 1/2. And so what you're going to do, we'll do it like this. Okay, we have x squared plus x. Now, y'all remember this is the chain rule, right? The chain rule, x squared plus x to the 1/2. X squared plus x to the 1/2. So you bring the 2 down, right? You bring the 1/2 down to make it a 1/2 right here. Then also you take the derivative of the inside piece. Okay. Now the derivative of this is just 1. Okay. So it looks like we may be getting somewhere. Y'all make sure you remember this. This is x squared plus x to the 1/2. Bring the 1/2 around to the front. This would be x squared plus x to the minus 1/2. It was in the numerator, right? So we're all good. And then remember the chain rule. Here it is, the chain rule coming back to haunt us. The derivative of this is this, right? Now, the question is, can we got two cold numbers here that survive all limits, right? But we still have this object that depends on x. So it's kind of hard to see where it's going here. Now, y'all, there's another way to do this that I could show you a little more formally, but just to save yourself some misery, just if the x wasn't here, the square root of x squared would just be x, okay? And you remember we had that rule of polynomials that says if the leading coefficients are the same, all you have to do is just take this number and this number, right? Okay? So what's really going on right here is you have something like 2x in here after the square root is being done. And then also this 2 would cancel. And so this limit, now I could show you some more algebra if you want to see more algebra here, but just think of this as the square root of x squared, all right? Well, the square root of x squared is just x. And so what you have is 2x over 2x here roughly. Now in the limit, this other term's not going to make any difference. And I'll let you get away with that, folks. If you want to do the algebra, it would involve dividing through by x, both terms, top and bottom. You know, but you'd have to divide through by the square root of x squared right here to get it to happen. But anyway, the long and short of it is this limit is just going to be equal to 1/2. Now, again, I feel a little remiss about doing that to you, but hopefully you trust me on that. And if you don't like me just waving my hands and telling you that, what you would be doing right here, you would be multiplying through by 1 over x here and 1 over the square root of x squared right here. Remember, the square root of x squared is x. And the algebra would show you that this all went to 1/2. Okay? And I do not mind you doing this, folks. It's just kind of a game. It clutters it up to show you the work. If some of you want to see it, I'll be glad to do another video on that. But for now, just understand the square root of x squared is just x. And so what you really have is 2x over 2x. And all these constants don't make any difference when you're doing these kind of limits. Okay? So this function kind of won the tug of war. It's tempting to think infinity minus infinity would be equal to 0. But this one was moving faster. And it moved faster to the tune of it winning out by 1/2, so to speak. Now, this would be a horizontal asymptote, and you can graph this, folks, on your favorite graphing device, if you have such a thing. You can graph this, and y equals 1/2. You would see it getting close to that, like on your TIs or whatever you want to do. If you have some extra time on your hands, you have to stay indoors. Punch this in either on Maple or your TIs, and you'll actually see that this thing tapers off towards the value y equals 1/2. Okay? Okay, wonderful. Okay, that's the first problem. Now let's take a look at the next one. All right, we got so yeah. Okay. Now let me copy this down here, folks. So you have a limit. Limit is x approach to 0 of what do we got here? 1 plus 2x raised. All right. There we go. Now, I copied down right? Yes, I did. Okay. Oops. I clean my glasses in about 2 weeks. Don't tell anybody. Okay, so you got minus 2. Get it? All right, good. Now let's take a look at what kind of obnoxious form this would be. Certainly as x approaches 0, this part on the interior just approaches 1, right? And if y'all remember the graph of 1 over x, this is actually in the form 1 raised to the infinity. Okay? Again, 0 right there just gives you the 1 that you see right here, right? Now remember, 1 over x, as x gets smaller and smaller and smaller, tends to infinity. You can see that numerically, or you can see it from the graph. Like say, for example, if x was 0.001, this would already be 1,000 right here, right? So definitely in the form 1 to the infinity, a million miles away from 0, 0, or infinity over infinity, right? Okay. Now, again, we got this obnoxious looking indeterminate form called 1 to the infinity. How can we manipulate this? How can we manipulate this form to make it look like that? Okay. So y'all, now this has taken me probably 4 years to figure out the best way to explain it, and I still wonder if it's the best way. But you're typically better on something like this to give it a name so you don't have to keep writing things down. But so what I'm going to do is I'm going to just call this expression okay, 2x. Okay. Now, what we're actually trying to find right here, let's just write it down, folks. And just from an organizational point of view, it might seem like I'm going to too much trouble here, but it's kind of hard to keep track of things. Okay, so we're trying to find the limit as x approaches 0 of y. Okay? Giving it a name so I don't have to recopy things. Now, it turns out it's quite useful to consider the limit. And I'm thinking some of you guys who've sat through calculus before know where I'm going with this. The natural log of y. Okay? Now, we're going to pay a price for this, but let me just get into the problem a bit, and so hopefully you'll see why we're doing this. Often when you have exponents, popping the natural log in there is a very, very useful idea. So let's just keep going here, keep on writing. Okay, limit. Now, y'all, the natural log, if we put the natural log here, that's going to drag this exponent around to the front. And so this is going to be 1 over x. Okay? And y'all take a look at that step. You see, y is equal to this. But if you put the natural log in front of this, that property, there's a property of exponents. You guys remember, how does that go? Natural log of anything, a raised to the, we'll say m. Cousin went there. So did my cousin's dad. They all bragged about it all the time. All right. So that's a and m. Y'all remember, that's just property. Exponents drag around to the front. Now, and that's what happened right here. Now, y'all, guess what? Do you see why that's important? Limit as x approaches 0. See how this little bad boy is going to come underneath? And we have ln of 1 minus 2x. Or 2x. All right, y'all? Hello. This means this, right, folks? But let's take a look here. Can you see? Can you see? The log base e of 1 is equal to 0. Just log base of anything of 1 is equal to 0, right? Remember, e to the 0 is 1. So this is in the form, and I'll write it out front so we can just keep going. So all of this agonizing effort results in a L'Hopitalable. Yeah, that's an adjective, L'Hopitalable, right? Don't you add able to anything to any noun to make it an adjective? All right, so we can L'Hopital this thing. Now, all right, so again, it's in the form 0 over 0. Now, y'all, a quick review. Remember ddx, natural log of any function. Technically, absolute values go there, but we really don't have to worry about that too much. Remember, this is equal to the derivative of the thing over the thing. the things or functions in our world. All right. Okay. See how this derivative rule, which we proved when I used to know you guys and actually get to talk to you, you just take the derivative of the function over the function, the natural log gets ripped out of there. Okay. Still, a lot of people, not a lot, some want to keep the natural log in here, but you see, that's the rule. The rule says if you want to take derivative of the natural log of some function of x, this is what it is. Okay. Well, guess what? We need to know that right now. All right. So, did I screw myself up here? No, I got enough room. Okay, now y'all, what is the derivative? The derivative of the thing over the thing is minus 2 over 1 minus 2x. Now, the derivative of this bottom piece is just 1. Isn't it so nice when things like that happen? Now, oops, y'all, what did I do? The mistake I made? No, I'm not going to give you credit for finding my mistake on this one. I'm just going to write it in there. We still got to write down the limit as x approaches 0. Right? Forgot to write that down, and it's tempting to do it. Now, y'all, what's up with this? This part certainly goes to 0. It's a trivial limit. You got minus 2 over 1. So the answer to this part of the problem is minus 2. But let's write down what this minus 2 really means. All that means is we know that the limit as x approaches 0. Remember, y is equal to this, right? Y is equal to this. The limit of, excuse me, let me write. What we've just proven is that the limit of the natural log of 1 minus 2x. Oh, I'm still on the screen. I noticed I was getting off the screen. You guys quite a bit. I missed out a little bit at the very end there. Okay. 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 That's what we've just shown, right? We've shown this, but we were interested in this limit, right? So how do we solve this problem? All right. Now, y'all remember that E and Ln are what we call inverse functions, right? So what we can do is exponentiate. You can do that with any continuous function. We're going to exponentiate through this limit, right? What we're getting right here, oh, come on. Get that. Okay, so limit is x approaches 0. E vaporizes this because it's its inverse function, right? So we're going to write down 1 minus 2x to the 1 over x is equal to e to the minus 2. Right? Golly gee. That was a very long path to Rome, wasn't it? But we've done it. Okay? Now, you guys, if y'all, depending on how much you're into math, what we've actually done is shown we have a definition of E based on the limit here. Notice that this minus 2 is all that came out of this, right? It came out. So you can see whatever this was. Let me write this down just for the. This is literally a definition of that mysterious number called E. What we could do is write this as 1 plus kx. Right? You see how the k is just a constant here? So what do you think I'm going to write down? Is equal to e raised to the k power. And if you follow this through, the minus 2 just kind of survived. That minus 2 survived the whole process, and you eat it through all of this work. Okay? So, y'all, this literally is a definition of e. You pick any number you want, and you can find e to the k using this limit. The practicality of this is you can just pick numbers close to 0 to get good estimates of e to any power. Like if you want to know what, say, e cubed was, put a 3 right there and then pick x to be maybe 1/10, and you would get a good estimate of e. An even better estimate if you picked x equals to 1/100th, right? So literally this is a definition of e. Now I didn't mean to, but it's e and pi and those kind of constants are probably the most prevalent, widespread constants in calculus and physics, science. So definition of e. Definition of e raised to the k. One of the many, there's others. Turns out you can change this to k over x raised to the x, believe it or not. K over x raised to the x as x approaches infinity. That's another definition of E, and you can verify that. In the name of time, I'm not going to do that. It's not time well spent. All right, folks, now let's get back to business here. So what I want you to do for your homework, I want you to do this one. And I do have another one here. And if I get good work on this that I know hasn't been plagiarized, and I'll tell you straight up, I'm getting some people turning in their stuff at the very last minute. Now, I'm not saying everybody that's doing that is guilty of anything, but it's awful odd that I got a lot of people turning their work in about 5 or 6 hours or even earlier. Then I have 3 or 4 who are like 3 or 4 minutes before the due date. It does make me wonder. Now, again, I'm not going to press it any further than that, but it'll all come around when you have to take the proctor final. All right. Proctor final counts 20% of your grade. So, again, I encourage most of you, and I think a high percentage of you are as honest as the day is long and you're doing your own work. But you're not doing yourself any favors to have a buddy in the class, in whatever you're doing, however you're communicating with them, and then turn it in late. And again, I'm not trying to point fingers at people who are just doing good, honest work and are pressed on their deadlines and turning in their work late. But there is a small percentage of you that have shown that pattern of waiting till the last minutes, and what do you expect me to think? Okay. It's a natural concern of mine to wonder what's really going on there. But in any event, the final will be proctored, and you'll have to show what you know there. There will be ways to monitor what you're doing a little easier. And so anyway, enough of that. Now, y'all, this last one really links together some of the stuff you've learned about the math of finance. Y'all remember the compound interest formula? The compound interest formula goes like this. Amount equals to principal. Okay, you guys may remember this friend of yours. It's called the compound interest formula, okay? That's the compound interest formula. All right, now, for a problem like this, you remember that n is the number of compounding periods. Like if you're compounding it annually, n is 1. You compound semi-annually, n is 2. Compound quarterly, n is 4. Compound monthly, n is 12, right? You can compound daily or nanosecondly if you feel like it, right? But what's going on right here is you can think of this as a limit problem. Now, if you remember, and I've seen some people really get excited about this, y'all, believe it or not just me. Remember our good friend PERT? P-E to the R-T? Okay. Y'all, guess what? Think about this as the limit as n approaches infinity, right? Remember, that's really what you're doing. You go from 1 to 2 to 4 to 12 to 365 days to however many seconds, in the limit, this is actually what you get. And I think from the previous problems, you can kind of see why. But y'all, if you'll work this and do good, authentic work, and you're submitting work I know you're capable of, I can help you out quite a bit on something other than the grade for this. Now, to make this fair, I can only give it to maybe the first 2 or 3 who submit it. This will be points to your lowest exam score. And I will, and I can, the thing just timestamps when you submit it. And I know it'll be like a feeding frenzy, but I'm only going to give the first 3 submissions. And if there's big gaps in those submissions, I'm going to wonder, okay? Really big gaps, or you wait till the end. But in any event, I will promise the first 3 submissions extra points on their lowest exam score. Now, what I want you to do is prove that this limit right here equals to this well-known formula called the continuous compound. This is called the continuous, if you guys remember. That's the continuous compound interest formula. Okay? Now, y'all, just one last hint on this. Your rates and your time are actually going to be constants here. Okay. Just think of this, because that's a fixed thing at the problem, right? It's after 3 years and the rate's fixed when you're actually doing one of these problems. But n will vary. N is going to go without bound here. So these are constants. So the odd's crucial. If you don't understand that R and T are constants, this problem is impossible. Okay. And y'all remember the derivatives of constants are 0, right? So that makes this thing immensely, the only thing that's alive is n. Okay, folks. So again, just to get it documented here, I will accept first three submissions. And y'all, life's cruel, but again, that's the only way I know to weed things out, because I've been spending a lot of time trying to track inauthentic work, and I'm being polite when I call it inauthentic. All right. So I'll take the first three submissions. So sorry if you're number 4, but that's just the way it's got to be done. And I can't think of a fairer way to do this, folks, unfortunately. Okay, first 3 submissions, and I will give you a +6 on your lowest. All right. All right, y'all. That is all. That is all. Take care. I gotta go eat a late breakfast. Take care.